Hello, in this video we are going to discuss the combination of resistances as well as maybe the combination of cells, that is the battery arrangement in the series of current electricity. So let's begin with the combination of resistances. Now in case of combination of resistances, we have two or even three. Two, namely the series and the parallel combination. The series combination and the parallel combination. Now in the series combination, it is the end-to-end combination. Or end-to-end connection. While the parallel combination is the common end connection. Now as we consider the third, it is a mix of series as well as parallel. So it is mixed grouping or combination. So these combinations are also called as grouping. So we have the mixed grouping. Mixed grouping, which comprises of the series and the parallel combination. Now, in case of series combination, what we have is, as you know, that the resistances are symbolically represented by these zigzag lines. These can be considered as resistance representing that of the entire conducting wire. We can also use this symbol for individual resistors. The resistors are of various shapes and types. We have the rheostat as well, which is somewhat represented like this, which has a variable resistance, so that is indicated by the arrow which can be dragged over the zigzag lines, giving the variation in resistance, but that is to be dealt later. This is the representation of resistance or even the resistor. We will be dealing with resistances of conducting wires, so this is the resistance. Now the resistance in case of series combination is the end to end, that is the one end terminating point that I have just pointed out with that bar over there, small bar. So that is the end point of the first resistance, which is the beginning of the next resistance, the following resistance. Like in this case, I'm just representing it by the bar just to show you, but there's no such bar in, we'll not be using those bars in diagrams to follow in case of circuits. But this is the, supposedly this is the end of the second resistance, which gives rise or is the beginning of the other. So this is end to end connection. The ending of one resistance is the beginning of the other, the beginning end and the uh, end point. So now as I consider the beginning and the ending of resistances, we can say that the current, suppose, is moving along that direction that is indicated by the arrow over there in a given circuit. Now this is a part of a circuit, of course. So in that case, we have the first end, that is beginning end, at a higher potential represented by the plus sign, that is the positive potential, and the ending point with a negative potential. Again, we have the first end of the next resistor at a higher potential, which allows the current to flow from the higher end to its lower end, along the conducting wire. So in each case, what we find is that, suppose this is having a resistance of R1, this is having a resistance of R2, and this is having a resistance of R3. Now in each case, as you see, because this is a single conducting wire which has been considered in sections as I have represented them, because this is a single conducting wire, the current in that wire remains the same across each resistor or each resistance. Now, as we know from Ohm's law, we have the potential as V is equal to R times of I. So obviously, with I remaining constant and I remaining constant, the potential will obviously be different across each resistance. That is, we have the potential across R1 as V1, across R2 as V2, and across R3 as V3, because R1, R2, R3 are considered to be different resistances, or resistances with different values, and they may be the same. If they are the same, obviously the potential across each potential difference across each resistance will be the same. That is, for R1 equal to R2 equal to R3, we will have V1 equal to V2 equal to V3 in case of series combination having end-to-end connection. Obviously this potential will be supplied across the circuit from a source. So this is the source with the positive end and the negative end indicated, and the potential has the EMF of the cell is, in this case, is V in case of no connection at the beginning, but then it, as it discharges to this discharges along the circuit, we have the potential differences across R1, R2, R3 as V1, V2 and V3. It is the same way that we had discussed about the combination of capacitors in videos that were made way back. Now in this case, as we can see, that this potential that was provided from the source has been distributed across each of the element, that is each resistance, in this case V1, V2 and V3. With those distributions available, what we can say is that if in case we had a single resistance in the circuit which was equivalent to the function of all those three resistors in series, having the positive and the negative end indicating the flow of current along the same line. So this is just an equivalent circuit of the above circuit, equivalent of the above circuit, which is giving the same amount of current for the same amount of potential that is available. We can say that V equals Ri, so R equivalent in this case times of I, that is the current flowing across the circuit. But what about the previous case that we had over here? What is value of V1? V1 is obviously I times of R1. V2 similarly is I times of R2, and V3 is I times of R3. So this is the value for the potential difference across each resistance. Now we use this and these values in this equation that is available to us. So what we find is, instead of V, I can use R equivalent times of I, that is for an equivalent resistance giving the same amount of current for when subjected to the same potential difference. We have the value of V1 as I times of R1. As you can see, I being the same in case of series, I can take it as common, I times of R1 plus R2 plus R3. I am skipping a step in between. Hopefully you can understand that. So the i's on both the sides can get cancelled out, and we have R equivalent to be equal to R1 plus R2 plus R3. So the combination of resistances in series The equivalent resistance is simply the algebraic sum of the individual resistances. Now, had these resistances been of the same value, then we would have had just 3 times of R. Let us say we have n number of resistances. Let us say we have n number of resistances in series, each having each with resistance R. Now each with resistance R means that we can just add them up. That is, the equivalent resistance in this case is R plus R plus R n times, n times, n times. So that means we have n times of R as the equivalent resistance in this case. Now this was the case of series combination. Now consider the case of parallel combination. So in case of parallel combination, what we have is a common end connection. In case of common end connection, what we can take is that the positive ends and the negative positive ends of each resistor is or resistance or conducting wire is taken commonly at one end, while all the negative ends are taken commonly at the other end, as is the case with parallel combination. So these are the resistances. I am again considering 3 of them in the beginning: R2, and this is R3. I just connect the positive ends if that were those were the positive ends, and the negative ends for the potential source V provided as I've shown in the diagram, and the current that was available moves across the circuit. Now as the current travels along this, with the potential difference that has been provided over here is the same, that is the plus end and the minus end obviously will have the same potential difference that was provided to the circuit. And as the potential difference across these two ends is the same, the potential difference across R1, R2 and R3, all of them will have the same potential difference for the common end connection, and that is the difference between these two, that is the series and the parallel. So with the potential remaining same, obviously for different resistances, if we were to have the same potential difference, the currents need to be different, so that when they get multiplied with the resistance, they will give the same product every time. So let us say that this is carrying R1, I1 amount of current, I2 amount of current across R2, and I3 is the current flowing across R3, such that we have I1 R1 equal to I2 R2 equal to I3 R3, giving us the same potential difference in case of this common end connection. And because of that, what we have is that R1, or we can say that we have I1 to be equal to V by R1. Similarly, I2 equals V by R2, and finally I3 equals V by R3. Now with these things available to us, what we can say is that in case, as we have seen in this case, the current initially was I, it was distributed as I1, I2, I3, which again recombined to give I after the negative end of the whiles connected in parallel, is it returns back to the same value I. Now from this we can say that I was simply distributed as I1, I2 and I3. Now if we were to consider an equivalent circuit in this case, such that we have an equivalent resistance which is giving us the same amount of current I across its circuit for the same potential difference provided, that is V, then we can say that V is equal to Ri, or R equivalent times of I in this case, and obviously we have I to be equal to V by R equivalent. Now with V by R equivalent being the value of I, we can just substitute those values in this equation that we have over here. Then putting it over there, we have V by R equivalent for I equals V by R1 plus V by R2 plus V by R3, and the V's on both the sides cancel out. The V's in the numerator of the right hand side can be taken as common and cancelled with the V on the left hand side, and all we are left with is the thing that I'm going to write at the bottom of the page. That is, we have 1 by R equivalent to be equal to 1 by R1 plus 1 by R2 plus 1 by R3. That is, the reciprocal of the equivalent resistance will be equal to the sum of the reciprocal of the individual resistances in case of parallel combination. Now again we are to consider another case over here, that is for n number of resistors of same resistance taken in parallel. Now in case of n number of resistors taken in parallel, what we have is 1 by R, they get added up to n terms, and that is why we have the final value to be equal to n by R. Let me just write that down for you. In case of parallel combination, what I have is that if n number of resistances having same value R are to be connected in parallel combination, what we have in that case is that 1 by R equivalent equals 1 by R plus 1 by R, that goes up to n terms. And in that case what we have is equal to simply 1 plus 1 plus 1 n times. So we have n divided by R with the denominator being the same in each case, the LCM sorted. So we have the, just taking the reciprocal of this, we have R equivalent to be equal to R by n. Now if you observe, this equivalent resistance is less than the resistance of the individual resistor or the resistance of the individual conducting wire. So in case of parallel combination, what we have is that the equivalent resistance is always lesser than the least resistance that is present in the circuit, while in case of series combination, because of the algebraic sum of the resistance for equivalent resistance, we have the equivalent resistance to be greater than the highest value of resistance available in that circuit. Now in case of two resistances connected in parallel, we just have a simple and direct formula which will be helpful in solving numericals. That is, we have, if we had two resistances, that is they are connected in parallel, then we have 1 by R equivalent to be equal to 1 by R1 plus 1 by R2 for two resistances in parallel. So in that case, we have R equivalent simply to be equal to, you can take the LCM on the right hand side, that comes out to be R1 times of R2, and then, okay, let me just do it for you in case you cannot follow. 1 by R equivalent is equal to R1 and R2 are the uh, in the denominator. For the LCM, R2 goes up and R1 goes up over here. So we have this R equivalent to be simply equal to the reciprocal of this thing, that is R1 times of R2 divided by R1 plus R2. It helps you solve numericals pretty quickly. So this is the formula for, considering the case that I've given right there at the top, that is R equivalent is equal to R by N. So let's just take this into account. If R1 was equal to R2, and let us suppose say that is equal to R, so we have, if R1 is equal to R2 is equal to, let us suppose say this is R, then we have R equivalent to be equal to R multiplied with R divided by R plus R. So we have R squared by 2R, so one of the R's can get cancelled out. So we have R divided by 2, that is R by N, N in this case being equal to 2. So it's the same thing given in a different way, but nevertheless will be beneficial in solving numericals related to bigger circuits that are to follow. And with this being the combination in series and parallel for a mixed grouping, what we have is that we can have resistors connected first in series, and I'm taking a 2 by 2 example, then another series, and then finally they are taken parallelly. So this is a mixed grouping, and a mixed grouping, obviously we can have resistances R1 and R2, R3, R4, and we know the formula. We can have a general formula for it, but uh, this just follows the same way. That is, uh, the values that I have taken, if different, can be a bit clumsy, but we can just take care of it. We have R1 plus R2 at the top. We have R3 plus R4 as the net resistance or equivalent resistance at the bottom because of the series combination. And finally, what we will have is that we have this will be the new circuit or the new equivalent circuit uh, in that case, where we have R1 plus R2 over here, we have R3 plus R4 over here, and we can just take them parallelly. And for two resistances taken parallelly, we have already given this. So the R equivalent in this case, although the uh, equation may look clumsy because of the unknown resistances or variables available, but still we can end up with an equation. We have this to be equal to R1 plus R2 multiplied with R3 plus R4. This is the resistance across each wire, equivalent resistance that has been considered for series. And then we have R1 plus R2 plus R3 plus R4 in this case. So this is a very generalized view of the circuit that I've just drawn, but on the whole we have a certain value now, considering the case of uh, we have a certain, if we have a certain value, then we can just use them. And this is for a 2 by 2. There are many more, not necessarily that you'll have m cross n where m is equal to n. You'll have very different kind of circuits that we may be doing in the numericals part of our video, that is to follow. in the numerical section, numerical playlist that I'll be discussing. Now we move over to the combination of cells. Now we had studied about cells in the previous video, and we can just combine them and see what's in store for us in that case. Now in case of combination of cells, we will have the same type of combination or grouping of cells or combination of cells. In case of combination of cells, we will be having the same series, parallel, as well as a mixed grouping. And the mixed grouping in this case will be pretty interesting, considering the case of a condition that we are to obtain, that is the condition for maximum current. Okay, so starting with the series combination, we have the series combination of cells, where the cells will obviously, as you know, end-to-end connection. That is, each cell, now the cells obviously have internal resistance associated with them, so that has to be taken into account. We'll see for that. So in case of series combination, you have the positive end of the cell and the negative end of the cell, followed by the positive end of the next cell, then the negative end of the other cell, and we can continue like this for n number of cells supposedly taken into account. We can say this is having the EMF as E1, this is having an EMF of E2, up to En for n number of cells in series, n cells in series. Each cell has an internal resistance. Now let the internal resistance in this case be R1, in this case be R2, again up to this term Rn likewise. And then we have an external circuit, this to be connected to an external circuit having an external resistance, suppose R, capital R. The current flowing along the circuit is I. In this case, we are just about to determine the value of current in this combination. Now, as the cells are arranged in a way where the positive ends are facing one end and the negative ends of all the cells, even though one after the other, are facing the other end, so all the cells are perfectly in series in this case. There may be a case where the cells are arranged in such a manner where the positive end and the negative end are like this, while another cell has a positive end and a negative end like this. But in this case, this is not a perfect series combination as far as the combination of cells is concerned. This will cause the EMFs to be acting oppositely, and as a result the net EMF in this case will be a subtraction of the lower from the higher. So if E1 and E2 are the EMFs of the cells, then we have for E1 greater than E2, we have the net EMF in this case to be equal to E1 minus E2, because they will be opposing each other, and obviously the net EMF is going to decrease in that case. No one really puts a cell in that form until unless you need to negate one from the other. But in general circuits, we have the cells arranged perfectly in series as shown in this circuit that I have just ticked, and the effective EMF in this case, or the equivalent EMF or the net EMF, is just equal to the algebraic sum of all the EMFs that are available, and that goes up to En. And similarly, with the internal resistances in series as well, we have just studied about the resistance. So the net resistance in this case for the internal cases is equal to R1 plus R2 going up to N terms. But what about the external resistance? That also is in series with all these resistances internally placed within the cells. So that is why we have the final net resistance as capital R net, which is equal to the external resistance plus the sum of the internal resistances taken in series. So now what we have is that the current that is flowing across the circuit is obviously equal to the net EMF divided by the net resistance, in this case being equal to, now we can use a summation sign over there. We have En extending from 1 to N in this case, and we have R plus the summation of R extending from 1 to N in this case. So this is a very generalized formula for the combination of cells taken in series. Now we'll be considering the combination of cells taken in parallel. First of all, we'll be using a condition over here because we will discuss another parallel combination of cells later after we have studied the Kirchhoff's law. In this case, what we are taking as an exception is that the cells that I have considered, although the cells that were considered over the series combination had different EMFs and internal resistances, here the exception is just that we are to consider the cells with the same EMF and the same internal resistance throughout in case of parallel combination, which is obviously the common end connection. So we have a cell over here with an EMF E and an internal resistance R, another cell of the same EMF and the same internal resistance. We are not considering different EMFs as of now. We will be considering them after we have studied Kirchhoff's law for your better understanding. So I need you to keep patience for that. And we can similarly have n number of cells in parallel for a general view of it. So n number of cells considered in parallel. That's more or less the way to draw it, I suppose. Here we have n cells. And the external resistance for the circuit is obviously capital R. Now, in case of parallel combination, you have the obviously the EMF. We have adjusted that to be equal across each wire or across each conducting wire connected to the common end. The current will obviously be the same in each case, but we are considering the net current over here. So the net current is simply the sum of all the individual currents that are to follow, but there is also an external resistance. So let's just check the value of the net current that is to be available. So in case of parallel combination of cells, what we have, the net EMF because it is a parallel combination, so the net EMF in each case is E. So we have the same potential difference across the positive and the negative end of each wire, and as well as for the external circuit as well, we have the same EMF that is E that we have provided for each cell considered. So that is E. Now the internal resistances, now in parallel we have n number of resistances in parallel, so as we had discussed, so this will be R by N. We had discussed this a few minutes ago in this video. And the net resistance with the external resistance taken into consideration, we have that to be in series with this entire lot of parallel combination that we have just considered. This parallel configuration is in series with the external resistance, so that is R plus R net. for series combination of that is R plus R by N. Now with that uh, done and dusted, we have the net current that is flowing across the circuit to be equal to E net divided by R net, as is the case every time. So we have this to be E divided by R plus R by N. The N can be taken as the LCM in the denominator part, so we have N times of R plus R, and this N that is down there can go up simply, and we have N times of E. So this is basically the value of the net current flowing across the circuit in case of cells in parallel, subject to the condition that each cell is having the same EMF as well as the internal resistance. As I said, for different EMFs and internal resistances, we'll be considering that after we have studied the Kirchhoff's law, which will be much easier to understand. And the next part carries the mixed grouping of cells, which is to be followed in the upcoming video, uh, where we'll be discussing the condition for maximum current. So how should the combination of cells, how, sh how should we have the combination of cells so as to obtain the maximum possible current in a given circuit? There's a different condition for that, but that is to follow in the next video. Till then, thank you. Goodbye.